Hello everybody, welcome back to another exciting video in Black Body Engineering. Today we have reached an important milestone. We're going to combine all the circuits that we built so far into one working CPU. So far we built the LEU, the register file, the instruction memory, the program counter, the data memory, and the control unit. Now it's time to connect them all of them together so we can execute real MIPS instructions. A quick recap of our old circuit. Before, remember, we built our program counter. This one is the responsible stepping through all the instructions. Steps through instructions. Then we build the instruction memory. This one stores and feeds the instructions to the CPU. We also build the control unit. This one decodes the instructions, and it also, because of that, it generates signals to the different components. We also build the register file. Remember, it's a 32 register file. This one stores operand and results. We also build the LEU so it can perform arithmetic and logic such as and or add and subtraction. We also build our data memory, and this one handles the load and store operations. So one way that we can put all of this together is by rapidly sketching our component that we have previously drawn. So for example, here we can have our program counter, and we have data that is going to be provided to our instruction memory. Remember, our program gets loaded to the instruction memory. We're also going to have a register files, or the file register. We're also going to have an LEU to perform our arithmetic and logic units. And we also going to have a data memory where we can store information and we can load it to. And this is our data memory. We're going to have an address going into. This is the result from our LEU. We're also going to have a control unit here that is going to provide the signals for all these components. So we can have a multiplier here to divide the instructions. So we're gonna have instructions, and if you remember, it's gonna be from bit 20 to 16. We're also gonna have data coming here, and some part of this of the instruction memory also is gonna go to our bit 1, and that's gonna be from 15 to 11. We also gonna have a sign extender here that is gonna extend the last 16 bit of our operation, and what we're gonna fit here is from 15 to 0, and the output of this one is gonna be 32 extended. We're also gonna have a multiplexer here, and the output of this one's gonna go there, and this one's gonna go here, and this is input A, B, this is input A, this is also gonna go here. We're gonna have information coming from our data memory, there's gonna be a multiplexer here, and this information is gonna come out and be fed into our register file. This information is gonna be extracted from my data memory. Well, the control unit is gonna provide different components and signals to different part of a circuit. For example, we can have, um, let's put that red. We can have a signal coming from here, be fed here. We can have a register write coming to our register file. We can also have another signal coming to this multiplexer. We can have here the LAU control. I can put it here. This is in charge of controlling the LAU, but then it needs the LAU up, and that's definitely gonna come from our control unit. And remember too that from our last 6 bits from our instructions, that's gonna be our functions, and this one is gonna be fed here, and then we're also gonna have another information coming to our data memory so we can read and write. So and we're also gonna have another bit to control the memory to register here. And yeah, and that's a quick sketch of our drumming of our drum, and this is our CPU 32-bit. So now we're gonna implement all of this in Logisim, and we're gonna see how everything behave and interact together. So let's go into Logisim. Let's see how it goes. So the way we're gonna start our CPU is by building our program counter. So I'm gonna use a register file, and I will use this one. It's gonna be a deep flip-flop. Actually, no, a register. It's gonna be a register, and this register is gonna be 32 bits because it needs 32 bits. We're gonna enable the write, so we have a little bit of control of our CPU, and we can say this is gonna be our enable button. And then we're gonna implement our clock because we need the clock. So where's the clock? Clock is right here. Actually, I can put it right here. We're gonna name it clock. And then this is gonna be fed into a splitter. We're gonna center it. And then remember that our ROM from previous video was not able to address all the 4 gigabytes of data. We were limited to a certain portion. We're just gonna use for our project 60 megabytes. I know that in previous video we made 128 megabytes, but we can be okay just by implement a 16 megabyte instruction memory. So because of that reason, this is our program counter. Let's implement now our instruction memory. For that, we're gonna use a ROM. ROM. This part is gonna be and memory of 16, actually 32, with memory address of 8. There you go. For this, we need a splitter to connect that part. So maybe we can reuse this one. We gotta face it to the west. We can only address 24 addresses. So 24, 24. And we can connect this too. And then this part is gonna be connected here. So now we have 24 addresses that our program counter can access. However, when it reaches this 24, we want our program counter to delete. For that reason, I want to implement a mux, and you see why in the put it together, because I want an additional input to be provided. This one. So my reset value is going to be entering on value 1. And then this is what's actually going to go to my reset. And then I want to implement a button so I can reset and swap between both. It's either gonna be, so my reset for my program counter either it's gonna come when address 24 is reached, or it's gonna be from my button. So I'll call this reset. And then I need a constant, which I'm gonna implement here. So as you can see, if I click it, then this constant 1 is gonna be fed into my program counter, and it's gonna erase it. Because if I do, I need a value here. As you can see, we'll put the value in a moment. So this is my program counter. This is my instruction memory. So now we have to implement our register file. Let me get this a little closer so it looks more aesthetic, stylish. So now that we have implemented our instruction memory, it's important to implement our register file. And remember, for our register file, we already had a circuit implemented for it. So the way we're gonna do that is we're gonna click our circuit, register file, and now we have a new element added to our register file. And we're gonna copy paste from our previous circuit our old register file, which we have here. Is fully implemented because we did it in previous video. You can also download it from the GitHub if you wish to. Now we're gonna back to our main circuit and we're gonna just drop it. And if you see, you can go into inside the sub-circuit and see your old implementation. So we go back, and now this part is a little tricky because not all inputs go, we have multiple inputs going everywhere from our circuit. Remember also that we are our instruction memory is by addressable, so we need to change that. So we got a quad. Now we can access multiple bytes at the same time, and now we can do a splitter. It's gonna be 30, it's gonna be 4 fans out and 32 bits. We can make it center and we can make it face west. Now we have to invert it because we have our big value on top because it's big Indian. Now we can connect these values here. As you can see, every information is readily available to our new. And now we need to split this information into multiple spaces. And for that, we're going to use another splitter. And we're going to use 4. Going to be split into 4. We're going to separate it. And we're going to make a center. So remember, our data is going to be divided into multiple segments. So our first one, it is divided between 31 and 26. So that's going to be our opcode. That's going to go to our control unit. Then our next one is going to be 25 to 21. Next one is going to be 20 to 16. And so to 16. And finally our 15 to 0. And this is going to be connected here. Our first 25 is going to be connected to my register 1. And the next one, we have to connect it to a mux. and that's gonna go to our register 2016 is gonna go to our first input, and then we can connect this information directly to our register file, and then we gotta split this one too into two values. Two, 16. We can separate it a little bit because it's too close to each other and I can barely see it. Then we have to fit the first values. This is our value that goes in here. We don't need this one. It's just gonna float for now. Our read register comes from here. And the data written goes here. We can implement our reset. It's gonna come from our reset line. And that's perfectly fine. Our clock signal also comes from the same place. We write data is gonna come from our data memory. So we're gonna leave it there as of right now. So now we can go ahead and implement our control memory. That control unit, we're gonna put it right here so we don't leave this one floating. So we can go ahead and connect this wire. So our circuits start getting, you know, like an actual CPU. So now our next step for our CPU is to implement our control unit. Our control unit is just another ROM that I implemented. And we're gonna place it right here that we have built previously. And we're gonna place it here on top. Maybe a little separate so we can use this space for more wires. And then this signal comes straight to our control unit. As you can see, it's already accessing our first address. And then we have to output our signals. We have a splitter, so I'll use this one. And then fan out 8. We need 9. And we're gonna separate it a little bit. Actually, that's too separate. Maybe 3. Sounds correct. Then center. And we're gonna output right here. We're gonna flip this over because I want my LEU operations on the bottom. To do that, we're gonna distribute ascending, then 1, 2, 3, 4, 5, 6, 7, and that's correct. And the way we're gonna decide which output is which one is by this instruction. So my first output, my A output is my register destination, and then LRU source memory to register white. So that's what each of this control line means. As you can see, the last two they're combined here is my LEU up 1 and my LEU up 0. So for example, my register write, that's my fifth line that is active right now. So 1, 2, 3, 4, 1, 2, 3, 4, and I need that output that is going to be connected to my register write. And then my register destination is also going to come through here. And that's going to operate this multiplexer. Then let's see. So perhaps the next step for our LEU will be to implement our LEU. And to do that, we need to port several of the designs that we previously built up. So let's start with our CLA. We need our CLA in our design. So we can go here, CLA. We'll port that one here that we previously implemented. We also need our overflow logic that we also previously implemented. We need the CLA2 that we also implemented before. We need our partial full adders. Now we can build the LEUs 4 bits. correctly porting over. So that one is ported correctly. But the OB logic, so okay. The I don't know what this is. That should be the circuit. I see some mistakes here. I think that will fix it. All right. So now from the LEU 4-bit, we can move to our LEUs. Okay. And now we can go back to our main LEU and then we can just drop our LEU. And now we have our own LEU fully implemented. So now that we have dropped our arithmetic logic unit, we got it connected to our CPU. So for our output 1, that's going to go directly to our A output input of our LEU. However, our B input goes into a mux. So we gotta drop one. And the way we're gonna do that is from here. So multiplexer, and this is gonna be 32 bits. And we can drop it right here. Actually, we can drop it right here. So the red input, and then the output of this is gonna go into our B input of our LU. And you may be wondering what happens to this input. So in order for us to get that input comes from the last 16 bits of our data word. So we gotta extract it from here because this line has 16 bits. And we need a splitter of 16 bits. We have to embed it. And this one is gonna go center. This is called the sign extender part because what we're gonna do is we're gonna convert 16 bits into 32 bits, and this last bit is gonna be replicated all the way to the bit 32, well, 31. So we make another one here. And we make that 32 bits. We embed it as well. And we're gonna attach this one to the last bits, 16 bits. We're gonna open it a little bit and we're gonna copy all of these ones. And then we can move this right here. And we can fit this line here. And we can fit the output of our sign extender right here. And this is our sign extender going into our multiplexer and being combined with the output tool for our register file, and this signal that is here is going to be the LAU source, and that signal is going to be this signal, and that's going to be our LAU source. And then these signals that are here are going to come from our LAU controller, and LAU controller is we're going to simply drop it as the LAU controller that we built on our previous video. So the way this is gonna work is we're gonna take it from our 16 bits. Remember, we only need the last 5 bits of our operation. But we need 2 inputs. One from the LAU up that comes from our controller and the function operations. So what we can do is get a splitter, and we're gonna turn this into 8 bits, 2 bits, 2 fans, and we're gonna space it a little bit. We're gonna make it face east and we're gonna center it and provide it here. So we need the bit 5 through 0 on top, and then we need the last two bits, that is our LEU up, that are gonna come from this side, and then this one is gonna be our function. However, before we do that, we need to split this signal and we need the last 5 bits, and that's what we need. So we have the LEU up coming from our controller, and we got the last 5 bits coming from our word for our function generation. Then we're gonna create an output for our LEU, which we're gonna turn it into center. And the last bit is gonna be our operation, and that's gonna be fed into our LAU. And then our first the first bit 3 is gonna be our A inverter, and then this bit is gonna be our B inverter. And this is the information going into our AU to control the operations. And then finally, after that, get this closer here. We can generate our data memory. And our data memory, with the output is simply gonna go directly from our LEU. However, you can see we have that problem again. So we have to manipulate our data output from our LEU and convert it to 24 bits. And then we can use this data, and this is the data we're fitting to. And then this is the clear signal. We can get this clear signal from the ones we have over here. Decided to reset. So when I press reset, it resets our data memory as well. Then we need a clock signal, and our clock signal is gonna come from this side, which we can also bring. And then we can get the output of our data memory. We can use another multiplexer. So we can make another multiplexer like this one. We can put it in front of our data memory. This is gonna be fed into one, and then the output of my result, the 32 bits, is gonna be fed back to our register file. To our write data, because this is how it loads the word. This is the load word instruction, and then this is the memory to register signal. So this one comes from here. Um, and then we have to finish our program counter. And in order for us to do that, we need a full adder that we're gonna add here. And remember, our program counter is gonna count by 4. Our input from our register is gonna come back, feed it to our adder. Then we need another one here. This one is in charge of the branching. And then we're gonna have another multiplexer here, which we're gonna connect here. The output of our full adder over here is gonna come and connect to this adder. Then this input, we need a shift left here, a shifter. 5 bits. It's gonna be a 2 because we need a shift twice. We're gonna fit that. The input is gonna be the 16 bits that we're getting from our word. That's gonna be the input when it's 0, and then this part is gonna be fed back to our counter. And then the signal from here is gonna depend on the result of our 0 output. So we need an adder, an AND gate, which face north. So one side is gonna come from our 0 values, and then the other one is gonna come from our branch, and that is this one. And that will be our program counter for it implemented. So output enable, that's gonna be our 4 because 1, 2, 8, 7, 6, 5, 4. That's memory read. That's gonna come from here. Write enable. Here, and that's it for our control unit. All its output signals are fully implemented in all the sites that it needs it. Unless I'm missing something, that should be the whole circuit implemented for our CPU MIP 32 bits. So now that we have completed our CPU, we can go ahead. I already wrote a little program that allows us to test the program on our branch circuit. So all I have to do is load it. Test program. You can see that if I scroll to the top, the program is loaded right here. So I close it, and then I go through the functions. So that's a bug that shouldn't be happening. So why is FFFF getting input into memory? Oh, I see I forgot to connect this input, and this one is the output 2 of my register file. So let's try again. Okay, I got a 7, I got a 3, 9, 1, 4, 8, 2, 6, and then it's adding the numbers together. Then, as you can see, we have 6, 2, 8, 4, 1, 9, 3, and 7, all of them added together. So we have x 6 plus 2 plus 8 plus 4 plus 1 plus 3 plus 7. Oh, it's already adding. Okay, I see. Seven plus 3 plus 9 plus 1 plus 8 plus 2 plus 6. I'm missing one more. I think it's 6. As you can see, 6 plus 2 plus 8 plus 4 plus 1 plus 9 plus 3 plus 7, it is 28. And store that value on 8. So our circuit is working correctly. So those are great news. And that means we're also implementing branch on these instructions. You can see sometimes this light lights up. So if I reset this again, maybe I can slow down the execution, maybe to 64. Enable. You can see sometimes it's blinking. That means our branch instruction is working correctly. but we do have one problem, is that our program is executing forever. So for that, we're gonna implement a halt instruction. If I reset this for a second and I go here, I have a halt instruction right here. So in order for me to implement that, I already have it here. I'm gonna tie all of this to an AND gate, because when I have all ones, I get a 0. So I'm gonna extract that from my whole word. And now I'm gonna end it. I'm gonna end my clock to disable when this is 0. And now, if I execute this program, it should stop once that instruction is encountered, this FFFF, because FFFF is gonna light up all the signals to 1, and in an AND gate, when everything is 1, I output is 0. So it seems I'm having a conflict of signals. It shouldn't be. Seems like our program is glitching out, and I don't know why. So let's see. Let me reconnect this wire again. Take this one out. This one goes here. This one goes here. That's the clock signal. That one connects to that one. Enable. Branch. That one. Now I should be able to auto click. Once it reaches FFF, all this lights up, execution stops. So my program has been halted and I have the result right here. If I can get closer, you should be able to see the data memory results. So 0 plus 2 plus 8 plus 4 plus 1 plus 9 plus 3 plus 7 is 28, which means our program was successfully executed. That means our circuit design is fully implemented. As of right now, I do not have the jump instruction installed, but it shouldn't be that complicated to install since it's still up here inside my branch. I And that's it. All the components we built so far are now part of a working CPU. This is for me a huge step because from here we can start running more complex programs. In the next video, I will try to implement the jump instruction and expand the CPU, probably add more instructions or maybe implement pipelining. If you are enjoying this series, don't forget to like, subscribe, and share with anyone learning computer engineering. Thank you for watching, and I'll see you in the next building. Thank you for being on our video of Black Body Engineering.